everyone. We're here talking with Diogo Alves about his recently peer-reviewed model, MicroAnts 2.5. MicroAnts 2.5 is an agent-based model designed as a base for more complex social and complex ecological models. So before we get too far into the model, Diogo, why don't you tell us a little about yourself?
Well, hello, Sean. Hello, everyone. So my name is Diogo. I work here in Portugal as a senior data scientist at the moment, and I'm also a part-time researcher. My field of interest in my part-time research, quote unquote, is agent-based modeling and complexity theory in general. I have a PhD in economics, and whenever possible and I have some free time, models to be more so this pretty much covers my background. Um, and yeah, so this and economic, if you could really couch it also in a general economic evolution setting. Where we have like different types of agents interacting with each other and with the environment. There are different selection pressures, meaning that if you increase the number of predators, for example, then the agents are going to fare like less well, let's say, and the ones that are more adapted to the environment are going to survive and prosper. So it's evolutionary in that sense. The agents have to interact with each other and with the environment and then prosper or die at differential degrees and rates.
So can you tell us a bit about your model and about the purpose of the agent-based model?
So yes, so some time ago, I read a book on written by a very effective science communicator called Rafael Lahoz Beltrán. So he's a Spanish professor at Madrid, and he's also a very effective communicator about these issues. And he's very passionate in particular about the topic of evolution. And so he wrote a book, which I have here with me, which is this one in Spanish. And I read that book and I was immediately entranced by that idea, and particularly in the model, a model therein that he explains really well, which was written in 1992 by Stephen Wright. Okay, so and this model was called appropriately MicroAnts 2.0, and this forms the basis of the model that I then wrote. And I was like, okay, you know, this model is really interesting, at least for somebody with my interests. Maybe not today, in an age where we have like agentic AI, this kind of topics of the artificial life has dropped a bit from public view, but it was big, in the early 1990s. And so Rafael was able to convey to me really well this enthusiasm, and I was like, you know what? Whenever I have a little bit of time and a lull from work, I have to really work on this, and particularly MicroAnts 2.0, like Stephen Wright wrote it. So this book has an MS-DOS emulator, and from there you can like interact and play with the models. And MicroAnts 2.0 is there. However, it's written in a very old language. It's very unwieldy to play around with. And so I was like, okay, you know what? I'm going to take this model, I'm going to extend it, and I'm going to publish to NetLogo so that the wider community can see it. And so this was my motivation, essentially. So it's essentially the story of two types of ants, but obviously, they're called ants just like they could be called zoids or boids or moids. It doesn't really matter. They don't behave like ants. And they're interacting with each other and with the environment. And then there's like ant eaters, and then they also have to be mindful of poison that exists besides food in the environment. Okay, so this is the story in a nutshell. Mm-hmm. I tried to port as much as possible from Stephen Wright's original formulation onto NetLogo. And I was very lucky in the sense that NetLogo affords us many of the things that Stephen Wright had to write in code in BASIC, I think. So you can see how old that thing is. And I was like, okay.
Wait, was there a copy of the original code available to you, or were you going based on his descriptions in the book?
So the code was not available. Okay. So and even the original model in the MS-DOS emulator where that model was, and all the other ones that Rafael published, they were in a CD-ROM. Okay, so and I was like, okay, I have to make this available to other people.
Yeah.
And And I have the tool, which is NetLogo, obviously like a very versatile language. And so I just said, you know what, I have a little bit of time now. I'm just going to adapt this model, extend it, and make it available to other people. And then hopefully either myself, because obviously my situation has changed some. So I'm now working full time, so I don't have the time that I used to have when I was writing this. But I still have the dream of extending it in different directions and making it MicroAnts 3.0. Okay, so I called it 2.5 because it doesn't differ enough from Stephen Wright's model 2.0. But it's already different enough to warrant its own version, but not 3.0 yet. Okay. So yeah, this is the story behind the model. Okay, so maybe I can show you very quickly. I can do share my screen and show you very quickly how the model works, and then we can potentially take it from there. So as usual, even this graphical representation was made to comply as much as possible with Stephen Wright's original formulation and his original code. You see that the agents, if I press setup, this is just going to populate. The blue, the gray dots are the anteaters, so the predators in the environment, and they move around because this is something that you can also adjust here. Okay. They move around, and then you have black ants, you have red ants, and then the green things are food. The green dots are food, and the brown dots are poison. Okay, and all of those things you can obviously adjust. You can increase the amount of food, you can increase the amount of poison, you can decrease it, you can change the color of the background, and all of these things are things that also in the original formulation of Stephen Wright you could do. Okay. Mm-hmm. Then you have different parameters. Which are not really that interesting, to be honest with you, but I can potentially just hit setup and just let the simulation run for a while, okay? And then I can explain things as they are happening. Okay, so I hit go, and then you see the anteaters moving, and then the ants are also moving around, and they are finding about their environment. And so one thing that happens is that, for example, for this particular formulation where you have anteaters behaving in a predatory manner, and by this I mean that they are sitting in one corner, and then if they see an ant, then they're going to chase it for a number of time periods. Okay. One thing that is going to happen is that at some point they consume all of the ants that are in one quadrant of the simulation, and then the remaining ants just explore corridors of stability. Okay, so they realize that they are outside already the reach of the predators, so they just move around in an area where there's little food, but there's also few predators. Okay, and this is one of the things that comes out of the model. Let me just quickly stop this. Is the fact that they respond like really well with emergent patterns to the behavior of the environment. Now, how is it that this works? So ants have a chromosome that fully encodes their behavior. Okay, so a chromosome with 16 places, a binary chromosome with 16 places that encodes for their field of vision, for whether they can see food or not, whether they can see poison or not. How is it that their sharing strategy is with other ants? How is it that they mate with other ants? Yes or no? Do they fight with other ants? Yes or no? And which ones? Okay. And all of this is encoded completely in the chromosome that fully determines their behavior. And so if you think about it, this is really an application of genetic algorithms. Only that instead of optimizing a complex nonlinear function, we're just optimizing and counting for optimization in survival in a hostile environment. Okay. And I'm happy to report I didn't do a full-blown sensitivity analysis as thoroughly as I should have. I'm ashamed to admit, but a good thing about this is that everything behaves as expected in a very mechanical way. Okay, so if you increase the number of predators, then the gene that rewards the seeing of the predator is going to prosper. Okay, and only ants that have that are going to reproduce more. As the environment gets more complex, for example, their vision range increases. So one possibility that we have in the chromosome for vision that encodes in the alleles that encode the chromosome for vision of the ants is that the ants are blind and they die very early in the simulation, especially if the environment is rough. Okay, so what we're seeing here is essentially an application of genetic algorithms where the behavior of the ants is fully encoded in the chromosome that controls what they do. Okay, so this is essentially it. And then on this left-hand side, you see this is something that is not afforded that is not present in Wright's original formulation because of limitations potentially in the language. But you see everything here, right? So the time series of the ants, the proportion of ants of each side of red and black that see the anteater, okay? And obviously, if you increase the number of anteaters and you increase the behavior of anteaters in terms of predation, more ants are going to start seeing the anteater as the ones that are not fit for that environment die off, okay? So this chromosome, number one, it fully encodes the behavior of ants, and number two, it controls their survival and their death. So this is, in a nutshell, just genetic algorithms, okay? Other things that the model allows you to do is to insert an ant in a simulation, okay? So you can, for example, you want to create a new ant and place it in the simulation and see how well it does. So you can change here, for example, let's say that you want the ant to be able to see 10 squares around it. And then you're going to change this, and then the movement is going to be horizontal. You could also put it moving everywhere or just moving sideways. Does it detect poison? Let's say that no. The mating threshold is a parameter that controls if the ant finds another one, then it needs to have a difference in energy to mate with the ant that it finds in a particular square. When does it share food? Does it share food with red ants, with black ants? Does it share food with red ants if it is red, and so on and so forth? And so all of this is encoded in the binary chromosome, but it's stuff that you can implement here and then insert in the simulation. And then you have that the ant has been inserted and you can follow it as it goes along. And this is something that was also present in Stephen Wright's code. Okay, another thing that I wanted to include in the model, and that was done, was that you can see, you can display the world's statistics in the Hall of Fame. So for example, here, in this moment of the simulation, you can see like the total ant population, red ants, black ants, the number of food, number of poison, how many kills has there been, how many red on red, red on black, black on red, black on black. And then I've also included the Gini coefficient, you know. So the idea is, like I told you, to essentially extend this model for more complex social simulations, okay? And again, there's no reason to think about these agents as ants. We can just as well think about them as like artificial constructs. And then, you know, it also puts like a hall of fame with the oldest ants, the ones that have the most food, the ones that have the most kills. You see that there's like a particularly violent warrior here with this chromosome that has had 3 kills. So it's like a serial killer. How many of them have mated? How many of them have shared food? And you see that there's a lot of sharing. And so there's a lot of stuff in this model to explore. So for example, here you have the sharing strategies and several different types of strategies for each type of ant, okay? So, and all of this is present in their chromosome. So this chromosome fully specifies their behavior. And then other things that, other things that the model allows you to do is that you can export these statistics as TXT files, okay, and export the plots. These are more legacy stuff. Legacy from Stephen Wright's code, because again, I wanted to make it as faithful as possible. And he has this in his code, and I thought, okay, you know what? It should be also in the NetLogo code, even though NetLogo has its own abilities to do this. And then you can also control other stuff like, do the anteaters behave in a static manner, whereby the anteaters are just stuck in a place, okay? And then ants just need to learn to avoid those places. Do they behave in a random manner? So anteaters just walk around aimlessly consuming any ants they find? Or do they behave in a predatory manner, like I told you before, where they just stay in one place and then the ants that fall within their field of vision are going to be persecuted and chased for a number of periods? So this represents the predatory pressure. And yeah, you have other parameters that can control for, you know, the pressure of the poison in the environment and so on and so forth. So this essentially controls the intensity of the environment and how well the ants are going to do. And again, this is a genetic algorithm writ large. Okay, so yeah, this is it.
Very interesting. I'm guessing the anteaters don't have any genetic algorithms of their own, right? Are they just sort of one
uh,
behavior?
yeah, they're purely reactive,
Okay.
but that is an interesting extension. Yes.
Yeah. So, and then do the red ants and black ants, do they share, or do they, I guess maybe that's a parameter, whether or not they mate or not, or are they separate, distinct populations?
It's also in the chromosome, right?
Okay.
There's the possibility that they have three different types of behavior. Okay, so you have the ants, you have their vision, you have their energy, and so on and so forth, their food stock. But they mate with each other and to produce new ants. They fight with each other, and they also share food with each other. Okay, so and there's also those behaviors are also hard coded in their chromosomes, and then you can also check how these behaviors change over time as a result of the pressure.
Interesting.
And one of the things that you can do is, um, for example, let's say, is it true or not? This is a possible experiment that could be conducted. Is it true or not that in very harsh environments, ants that don't even share with their own culture are going to die off? You know, so you have a little bit of like altruistic versus egotistic behavior here. So
Yeah.
you could, as you vary the selection pressure, you can see different behaviors, not only the traits of the ants, but also their behaviors with differential rates of survival, which is a very interesting thing.
I'm guessing then do the individual populations start off with very similar or identical chromosomes?
They're completely randomly assigned, so
Okay.
like in a genetic algorithm, and then we
Okay.
let just evolution weed out whoever is going to lose. But it would be interesting actually to see like a very uniform population that just differs in a chromosome or two, and then see whether the other behaviors could evolve. That's
Yeah.
also interesting.
Yeah.
You're absolutely right. Yes, that would
Very
be
interesting.
an interesting thing to put.
So, uh, I guess you sort of already described. It seems like the main challenge in developing this model then is interpreting the original work and putting it into NetLogo. Is that a good summary?
Yes. So there was, on one hand, I had a very good guide, which again was no, Rafael's book.
Yeah.
If you know
We'll include
Spanish,
the citation in the somewhere too.
yes,
But yeah.
absolutely. So on one hand, I had that very good guide, but on the other, there were also things that I had to fill in the gaps for myself. Absolutely, because it's not a full description, and I did not have access to the code.
Mhm.
So I had to port it as is. I played around a lot with the original model, okay, the one that comes in Rafael's book. But obviously, there's always going to be gaps that need to be filled because the devil is in the details, and in this case, very much so. So, but it wasn't a lot. I'm very happy to report that I was able to more or less guess what was happening in 90% of the simulation.
Um, so are there any insights from the models that you want to highlight?
Um, there's a very interesting emergent pattern that for certain degrees of predation of the anteaters, this was something I was not expecting, but you know, when you're developing a model of this sort, you always try to maximize the bang you get for your buck. And models like Sugarscape, for example, just to give, because it's in the same vein, you get a lot of bang for your buck, and here you don't, because the code is somewhat involved. It's not for the faint of heart, to be honest. Um, so you get a little bang for your buck here. You get more in Sugarscape. But one of the things that was very interesting was that there's emergent patterns of flocking for certain patterns of predation for the anteaters, right? So if you configure this just right, you can see that some ants are just going to aggregate with each other, and they're going to form very stable bundles of like a proto-society of ants, even
Hmm.
of different colors. I haven't formally tested this, but it's something that's always come up whenever I tune this just right. And this is good because it's an emergent pattern that I was not counting on. I did not see in the original model when I was running it. I mean Stephen Wright's model. I did not see that, but it's possibly because in his original formulation there's only one anteater and it moves around randomly. So
Okay.
the fact that I allowed for this extension of multiple anteaters that can have predatory behavior is something that may have driven ants to aggregate with each other and forming proto-societies where they just move in tandem. That was very interesting to see.
It also looked like you have it set up, your model set up as a torus right now. Do you know if the original model used sort of uh, a flat non-torus shape or regular shape or a torus?
Uh, that's a very good question. I would say that they do, because sometimes you have ants falling outside of the simulation and they show up from below, right? So it's
Okay.
like a complete wraparound. I would say that
Yeah.
yes.
Yeah. Okay. Really interesting. Um,
Thank you.
so I guess what you mentioned MicroAnts, a hypothetical MicroAnts 3.0. What's next with the model, and I guess, or what sort of things do you hope somebody else might expand upon in the future?
So in that info flap of the model, I have placed some suggestions. But when I saw the script, I was like, what I would really like to do is to implement some sort of social evolution and social learning. There's a model in COMSIS written by Dale Briarcliff and a colleague of his that is about fitting sugarscape agents with learning abilities. It's called Implementing Machine Learning in Sugarscape or something to that effect. Don't quote me on that, but it's something to that effect. And I was like entranced by that idea, and I was like, I would like MicroAnts to have some sort of social evolution. And what I mean by this is that, as of now, like I told you, the chromosomes fully encode the behavior and the strategy of ants. And then we just let evolution play its course and they behave completely deterministically, even if there's some emergent patterns. But something that would be very interesting to have is to have some sort of social learning whereby ants are not forced to do anything, but we just let their behavior emerge. So, for example, let's say that an ant has a field of vision of 10, and then it sees food within its field of vision. It doesn't have to go there if, for example, the number of enemies it sees around the food are too big. Okay, and that is something that could be done potentially via feeding this model with a social learning module, where you have like different cultures of ants that trade information among each other. This could be done with, like, for example, genetic programming, where you have the terminals as the actions of the ants, right? So, for example, a rule that could evolve is if food in neighborhood is bigger than 10, then don't move there, or something like that, something to that effect. So, and like this, we would have biological, quote unquote, evolution and social evolution in the same simulator. And other things that could be done, for example, is we could have one type of ants with social evolution purely and another type of ants with biological evolution purely. And we would have to have a situation where the social evolution happens a lot faster than the biological evolution, just like in the real world. So this is an extension I would really like to implement, and I'll try to do it as soon as possible whenever I have some time. But yeah, so social learning is, I believe, where the difference between 2.5 and 3.0 is.
Very interesting. Yeah, I imagine too that in addition to the speed, you'd have sort of a quick uniform change with social evolution, and that the ants might all sort of pick up on one rule very fast, as long as it's working properly, or as long as it's helping them. So
Uh, can you repeat that? Sorry, Sean.
I was just thinking to myself that in addition to it with social evolution, in addition to the speed of the characteristic spreading, that you might end up with sort of very uniform changes very fast in the way that human culture sort of, we all sort of follow each other's behaviors, or follow the societal norms. And so, if it makes sense for that ant to, use a vision of 10 or not see enemies within a vision of 10 of food and be successful, then all the ants would quickly adapt that. So, um,
Yeah, yeah,
they might essentially all behave very, very similarly very quickly. I guess.
yeah. True, true, true. Yeah,
So,
you're absolutely right. But
yeah.
even seeing, even that would be an insight, right? So
Yeah.
how fast is a rule going to evolve? And then something that we could have is like outputting the result of the GP as the rule, and that would be like the proto rule of a society. Something
Mhm.
like if you see an anteater over there, please don't approach it. Something like this. You see?
Yeah. Yeah. Well, this is really cool. I appreciate you talking to me about this model, and look forward to seeing version 3.0 someday.
The pleasure's all mine, and thank you for this.
Of course.